Good afternoon. Welcome to this month's CAPE Advanced Technology Lecture. It's a great pleasure to welcome Professor Hong-Seok Lee from Seoul National University, who is going to give the lecture today. Professor Lee received his bachelor, master, and Ph.D. degrees, all in electrical engineering from Seoul National University in South Korea in 1993, 1995, and 1999, respectively. After his PhD in 1999, he joined the Samsung Advanced Institute of Technology in Suwon, South Korea. And in 2016, he became a master, which is the equivalent of a vice president of technology in Samsung Electronics. He stayed in Cambridge as a visiting researcher in CAPE and in 2011. He has been working at the Seoul National University as a collaboration professor since March this year. His research interests are optics and photonics, in particular, novel optical devices and systems with micro-nano structures. His recent main research area are the next generation 3D displays, such as holographic displays and AR/MR glasses. The talk of Professor Lee will be on the holographic flat panel display today. Professor Lee, please.
Thank you, Professor Chu. Today, I'm going to talk about the holographic display, especially with flat panel form factor. Displays trick people with technology. So far, it works well in two-dimensional space. We watch full-color video clips with various devices, TVs, monitors, and smartphones. With 60 still pictures per second, we thought objects on the display move continuously. We can see full-color objects by mixing only 3 RGB color pixels. How about 3D display? As you can see in this figure, there are ups and downs in 3D displays. Sorry for the Korean characters. Third wave was around 2010. Around that time, a lot of 3D movies released, including the famous movie Avatar. We live in 3-dimensional space, and we have 2 eyes to tell the distance of the object from us. So the strong demand for 3D display is natural. We have to find a technology to trick people in 3-dimensional space. The problem is that it is hard to fool people in this case. We sense distance from an object with these 4 physiological depth cues. We have 2 eyes about 65 millimeters apart from each other, so we see a little bit different images from them. Our brain knows the rotation of our eyeballs and the thickness of the lens in the eye, corresponding to the distance when we see an object. If there are some mismatching in these depth cues from the 3D display, it gives us very uncomfortable feeling. So to trick people thoroughly, we have to make a 3D display with proper depth cues, all 4 of them. A conventional stereoscopic display gives only binocular parallax and versions. The stereoscopic display shows 2 slightly different images for left and right eye. This binocular parallax gives us 3D perception. When the displayed images are on the screen, the lens of the eye focuses on the screen. Then we perceive the 3D object position is off the screen. The eyes try to focus on perceived object position, then images become out of focus. So the eye tries to focus on screen again. And this sequence goes on and on, and the viewer feels visual fatigue. It is so-called AV conflict, accommodation versions conflict. On the contrary, holographic display can generate whole physiological depth cues, so it gives natural and realistic 3D perception without any visual fatigue. When you think about interactive 3D display applications without proper accommodation cue, the 3D display causes a trouble to interact with virtual objects by hands. It will be more serious issue when you touch and manipulate virtual objects with your hands in the metaverse in the near future. So it becomes more and more important to implement all the 4 depth cues, especially accommodation. That's why we think about the holographic displays. Then, how can hologram implement all the depth cues? Hologram uses wave nature of light, which means it uses both amplitude and phase. The light from the pixel of the conventional display has no phase control. It cannot make a tight focused spot in space like this. But if we know the phase of the input beam, and anyhow we can control the phase of each pixel, then we can make a tightly focused spot. And also we can make many 3D points in the space by multiplexing them. Finally, that becomes a holographic 3D images. Like the origin of the word hologram, recording the whole information of light. The classical hologram is recorded in the holographic plate, which contains the entire visual information of the 3D object as a fringe pattern of interference. As you can see in this picture, it shows realistic, vivid 3D images. But we have to use real objects to record a classical hologram, and the post-processing is needed. That means we can get only still images. Then, how to make a moving picture holographic display? Due to the hologram's outstanding ability to represent realistic 3D images with accommodation, there are various types of holographic displays according to the applications. Today, I'm going to focus on the holographic flat panel displays. For holographic flat panel display, we need only 2 devices. One is a coherent backlight unit, which is an area light source of coherent beam. Slim form factor and high optical efficiency are the main issues. To make a slim backlight without losing coherence, we can use reflection, refraction, and diffraction, not scattering. The other one is an SLM, spatial light modulator, which can control the phase of each pixel. Total number of pixels, that is space bandwidth product, has become the bottleneck of SLM for hologram. We need small pixel pitch for wide viewing angle, and we need very large number of pixels with this small pixel pitch for the reasonable display size. And one more thing we need is CGH, computer-generated hologram. Hologram calculation should be done in real time with reasonable computing resource. As I mentioned, there are challenges to overcome for holographic flat panel displays. I will talk about these 3 challenges and our approaches. First one is about viewing angle and display size. Viewing angle is determined by the pixel pitch of an SLM. Classical hologram recorded as an interference pattern by signal and reference beams. It has wide viewing angle. There is no defined pixels in this case, but we can guess the virtual pixel pitch from the viewing angle with this equation. The virtual pixel pitch is on the 250 nanometer, and display resolution is over 100,000 pixels per inch. We need enormous number of pixels a large screen size in this case. In this point of view, we should consider the total pixel count of the SLM. This is SBP, space bandwidth product. For the flat panel display larger than 5 inches, I don't think we can have enough SBP for over 100-degree viewing angle. We have symbolic number of pixel pitch for hologram, 1 micrometer, which gives us around 30 degrees viewing angle. 30 degrees seems to be not enough, but it is okay for the mobile applications. Researchers at ATRI in Korea and NHK in Japan had already made 1 micron pixel pitch, and they showed good results in a small SLM size. But if you could make a 8K by 4K display with 1 micron pixel pitch, the size of the display would be only 8 millimeter by 4 millimeter. You can imagine the difficulties to make it bigger, over 5 inches. Anyhow, if we could have this high SBP panel, then optical architecture will be very simple like this. A simple collimation backlight with light source and the SLM are enough. That's all we need for 30-degree viewing angle. But unfortunately, even considering the projected progress of display technology, it is not possible to get on 5-inch or larger SLM with higher enough SBP. We have to use an SLM with moderate resolution. For the mobile applications, 5 to 10-inch displays with 500 ppi or 1000 ppi are available these days. With this pixel pitch, we can see only the part of the display due to the narrow viewing angle. After introducing a field lens, we can see the whole display, but we can see the whole display only at the focal position of the field lens. So we need a special function added BLU, which can steer the light when a viewer moves. Introducing field lens and the function added backlight can overcome the SBP limitation of the SLM. Second one is about slim form factor. We implemented the holographic display prototype as a proof of concept in 2015. It consists of a conventional 10.1-inch liquid crystal display, a large bulk field lens, 2 fiber-coupled light source, and mechanical steering system consists of a huge delta robot. We used free space to expand the beam size of a 10-inch, and for the calculation of hologram, a high-performance PC with multi-GPUs was used. The result is shown in this movie, which is really good in image quality without any visual fatigue. We had successfully implemented a holographic display proof of concept. Next question is how to make a holographic flat panel display, how to make it slim. All the bulky and thick components in the prototype need to slim down. Thin lens using geometric phase, backlight using waveguide, and slim beam deflector using liquid crystal technology are introduced. The third one is about the real-time generation of hologram. To calculate hologram, we need a lot of computing power. That's why we use a high-performance PC with multi-GPUs. But it is too big to be a part of flat panel displays. Considering the computing power needed, it is not likely to get enough resources to calculate holograms from AP in mobile applications, even though AP's performance is improving very fast these days. We should prepare a dedicated ASIC chip for this purpose. We successfully developed a dedicated hologram calculation hardware with a single chip FPGA, and it could replace the high-performance PC. Now, let me talk about the implemented slim-panel holographic video display using previously mentioned approaches. Slim-panel holographic video display consists of a steering backlight unit, a geometric phase lens, a spatial light modulator, and a holographic video processor. The steering backlight unit is called S-BLU, which consists of a beam deflector and a coherent backlight unit. The S-BLU is the key component for expanding viewing angle of a holographic display. It steers a small original viewing angle to the viewer's eye position, which is detected by eye tracking device. We proposed S-BLU that directly modulates the coherent light to steer the optic axis of backlight, so it can deliver the holographic image to a desired direction to the viewer. In S-BLU, additional phase array called the beam deflector is included. So two diffraction matrices, SLM and BD, are stacked together. In this case, the space bandwidth product will increase by the ratio of the pixel pitch of SLM and BD. Since BD has a one-dimensional electrode structure, it is easier to implement relatively small pixel pitch compared to the two-dimensional SLM. The pixel pitch of the BD is designed as 2 micron, while the pixel pitch of the SLM is 58 micron. Then the effective SVP is increased about 30 times without increasing the number of pixels in the SLM. Beam deflector steers the transmitted lights optically like a prism, and it is controlled by electrical signal on liquid crystal. Its angular resolution is about 0.02 degrees, since we have 720 independent channels to apply voltage on each electrode. At the top right, you can see the point of the light source is moving by the beam deflector. The coherent backlight expands beam size by passing through the waveguide. Two gratings with the same pitch are imprinted on the surface of the waveguide. These two gratings, input and output gratings, conserve the angle of input and output beams steered by the beam deflector. Since it is difficult to optimize both the efficiency and the uniformity for 3 colors at the same time, C-BLU consists of 2 BLUs. One is for red and green, the other is for blue. The total thickness of the 2 BLUs is about 6 mm. The surface grating pattern on a C-BLU is fabricated by nano imprinting lithography. The duty ratio is controlled along the waveguiding direction to ensure the uniform output distribution of the backlight. An algorithm for real-time hologram calculation can be divided into 3 main steps. In the rendering step, the rendering engine produces the 3D scene into color and depth image data according to the measured eye position. Because this process was implemented using a commercial game engine, Unity, anyone can easily create 3D hologram contents. In the second step, a hologram on the SLM plane is calculated using color and depth information obtained in the previous step. Propagation equation is used to obtain the field data on the pupil plane and then the field data on the SLM plane. Propagation equation consists of two-dimensional inverse Fourier transform, so it requires a lot of calculation resources. The last step is converting the complex field of SLM into the positive integer data. We use an amplitude-only SLM, which is a commercially available liquid crystal display, so it is necessary to encode complex valued hologram to positive integer with little degradation of information. In this slide, I'm going to explain the propagation step which required a large amount of calculation. The left side is an estimated computational power requirement for implementing a real-time 10-inch UHD hologram with a 30-degree viewing angle. Assuming that the pixel pitch is 1 micron, 27 gigapixels are required for 10-inch SLM, and UHD 4K point cloud data are calculated using Rayleigh multiplication. The required amount of calculation for real-time hologram is roughly 2.5 zettaflops. It is not feasible to calculate this using mobile phone or PC. In our Slim-panel holographic video display, the viewing angle of the SLM is quite small due to the large pixel size. Small viewing angle helps to reduce the computational cost by 31 million times due to the small number of pixels to be calculated. And we use depth layered method rather than point cloud, so only a finite number of distinguishable depth layers to be calculated. And again, using optimized Fresnel allocation can reduce another 40 times in computation. The computational cost is reduced by about 10 to the 12 times in total. We confirmed the real-time calculation is possible using 3 Titan Black GPU by applying all these methods. We also implemented a dedicated hardware IP for this and integrated it into single-chip FPGA. Various methods were applied to lessen the burden on hardware. If you use floating point, the accuracy of the calculation is maintained, but it requires a lot of computational resources. All calculations were modified with fixed points. To maintain the image quality, the size of the data in each step is checked and adjusted, not to be underflow or overflow. Next, we optimized the FFT core to switch between 1K and 2K. This reduced a lot of hardware resources because it is the largest part of the hardware implementation. And frequently used constants calculation based on sine and cosine function were optimized in the form of the lookup table. The last one is frequency filtering. The size of the logic is directly connected to the real-time calculation, and also the bandwidth of the bus must be considered for it. After the first FFT, the intermediate results need to be saved. At this point, data is transferred to memory through the bus line. Too much data will cause bottlenecks and slow down overall computation. To minimize this, the frequency range, which has an important effect on image quality, is cropped and stored. Therefore, the amount of data moving to the memory via bus can be reduced, and the speed of calculation can be increased. This hardware IP was integrated into single-chip FPGA, and we can show the real-time color hologram with 0.33 TOPS calculation. Here is the result of real-time holographic video. The holographic scenery under the ocean is generated in real time. One can actually control the motion of the turtle using a keypad. In the bottom, the turtle hologram are taken to check the motion parallax according to the angle of the observer. There are several things to be improved. First of all, the efficiency is still very low compared to 2D displays. The overall optical efficiency is on order of 10 to the -6. It is mainly due to the large number of optical elements consisting of the holographic display. We are trying to adopt the monolithic design to minimize in and out coupling losses. Merging pre-expander and backlight unit into a single substrate is an example. Anti-reflection coatings and index matching also help to reduce the reflective losses. Replacing the surface grating with volume grating or geometric phase optics can help to increase the diffraction efficiency. Even though we have expanded the viewing angle by 30 times with S-BLU, the viewing angle of 15 degrees is still not enough as a commercial display. So reducing pixel pitch of the beam deflector less than 1 micron is needed to expand the viewing angle over 30 degrees. From this slide, I'd like to talk about what is needed to commercialize holographic flat panel displays. In addition to developing the holographic flat panel display device itself, establishing the ecosystem of hologram contents are also important for the commercialization of holographic displays. From the content creation to the display, we need to develop various devices and technologies. In the next few slides, I will discuss a few selected topics that are highlighted in this chart. Regarding the content creation, the various types of cameras have been studied and developed. Unlike other conventional 3D capturing systems, such as RGBD camera, incoherent holographic camera can directly record the hologram of the real world. Therefore, no further processing is required, and the captured hologram can be directly displayed as CGH. One type of incoherent holographic cameras is called self-interference digital holography. This system induces the self-interference of the waves coming from a single point source, and the impulse response function contains the depth information of the point source. When a 3D object is given, the camera captures the incoherent summation of impulse response functions from multiple 3D points, and the resulting hologram can be treated as a conventional CGH. Recent development demonstrates that single-shot real-time hologram capturing is possible. In the near future, we expect to have holographic broadcasting systems, hologram captured by a holographic camera under incoherent environment, and it is transferred to and viewed on holographic displays in real time. The hologram requires a coherent aerial light source as a reference beam. However, the high coherent light source typically induces strong speckle noise. On the contrary, the low coherence of the light source adversely affects the sharpness of the image. So far, there has been no proper light source for the holographic display. It provides speckle-free and sharp image features. One possible approach of making an ideal light source would be placing multiple light sources inside a small area. In this regard, the visible range pixel can be one of the most promising candidates, because each pixel cell exhibits slightly different wavelengths and has no correlation with each cell. The speckle noise will decrease by a factor of 1 over square root of the number of the light sources. With this approach, the small bandwidth of the overall envelope in wavelength domain can provide sharp holographic images. Even though we can compute the ideal hologram from CGH algorithm, we lose some information when we encode the holograms according to the data format of the SLM. For example, conventional SLMs can either modulate only amplitude or only phase. For amplitude-only SLMs, we have to extract the real part of the computed hologram. Mathematically, this process is equivalent to adding the conjugate counterpart to the hologram, and it inevitably induces the unwanted conjugate noise and DC noise. For the phase-only SLM, this type of noise can be avoided using iterative algorithms, but they require additional computational power. Ideally, we want to have a complex SLM which can fully express the amplitude and phase in each pixel, because such device can show noise-free 3D holograms. One solution to realize a complex SLM is to use two-phase encoding method. There are other approaches as well, and I hope to see a complex SLM with simpler architecture in the near future. We already have the real-time CGH generation solution for holographic FPD using an additional dedicated hardware, but ideally, we want to compute CGH in real time without dedicated processor. Regarding the computation of CGH, there are two major challenges. We need to generate CGH in real time, and we also need to compensate the system artifacts. Deep learning has been proven to be a very effective tool for addressing these two challenges. MIT demonstrates that the real-time generation of photorealistic CGH is possible with 60 Hz on GPU and 1.1 Hz on iPhone. Regarding the system artifacts compensation, Stanford research team has shown that incorporating the captured images into the CGH computation can dramatically increase the image quality. They combined this so-called camera in the loop approach with deep neural network and demonstrated real-time generation of phase-only hologram with enhanced image quality. The ultimate goal of this line of research would be to generate CGH in real time on NPU, so that holographic displays can work on power-efficient portable systems. Let me conclude my talk. In the near future, you will see the holographic display on the shelf of the market. We have solved many challenges so far, but there are still issues remain, such as limited viewing angle and large power consumption. We expect that those problems will be solved by researchers all over the world, including participants in this lecture. It would take years to develop practical holographic flat panel displays, but that does not necessarily mean that we should wait for a long time. We can devise holographic devices for specific purposes with some limitations and constraints of current holographic displays. For example, stationary devices such as robot plates, hologram agent, vehicle displays can be commercialized earlier. Those holographic devices will give us an upgraded 3D experience and allow us to have more realistic communication with each other. As the ecosystem and supply chain of the holographic display are growing, the new technologies and devices that go beyond the conventional displays will be required. There are a lot of opportunities for research and business in this field, and we hope to see many interesting ideas in the upcoming years. In our daily lives, we are surrounded by three-dimensional physical world and also by three-dimensional metaverse. And our eyes can see 3D information, so the ultimate display should be able to handle 3D visual information properly. It is no doubt that the holographic display is the best candidate. Thank you for your attention.
Thank you very much. This is a fantastic talk, and it not only showed the significant progress you've made and pushing the technology very closely to the products commercialization, but also covers all the end from the technology ecosystem to system design and to different implementations, different aspects. I'm sure a lot of people will learn quite a lot from it. Now,
I hope so.
talk is open for questions.
So, hello, Professor Lee. So actually, I have a few questions. So maybe one by one. So actually, thank you very much for such nice and inspiring talk. So the first question is about this beam deflector you made. So my question is about the diffraction efficiency. So normally, as far as I know, such, for large angle, as angle increase, I mean, the diffraction efficiency basically decrease a lot.
Right. Diffraction efficiency is based on the diffraction. So it's the efficiency is decreased by the angle increases. So during this experiment, we use image processing to compensate this degradation.
Okay, I see. So
yes, we use. Okay, go ahead.
Can you wait for people to finish, please?
Yeah, sorry.
Yeah, Professor Lee, yeah, please.
Okay. We use image processing, which means we reduce the right direction of image is lower than side image. Can you understand me?
Yeah, maybe I understand.
Okay.
So basically, maybe you kind of, I mean, you have eye tracking. So basically, within the FOV, you have to basically also change the intensity of the backlight. Oh,
right. So there are two ways. There are two ways to control. One is control the intensity of a light source. The other is beaming the image brightness. So we use the second one.
Okay, I see. So the second question is regarding the manufacture of the large-scale beam deflector or SLM with high resolution. Actually, you also mentioned the Korean group ETRI. Maybe just recently they released a 3-inch SLM on glass with 1 micrometer pitch size. So my question is it possible to make, for example, much larger, for example, 10-inch SLM with such high resolution? And the second one is, so if the pixels go down to 1 micrometer, so basically they have a strong crosstalk between neighboring pixels. So we have to solve the fringe field effect. So how can people solve it?
Okay. Actually, in my opinion, large size 1 micron pixel pitch is very hard to make. So they already make around 3-inch 1 micron pixel pitch. Atri make 1 micron by 9 micron rectangular shaped pixel. They make it. As you mentioned, they have a problem of fringe effects. So that's the problem to make how to say big SLM. So in my opinion, that's not possible. For example, as I mentioned in the presentation, 1 micron pixel pitch with 5-inch inside the 5-inch is not possible. It's not just because the fringe effect of liquid crystal. One more problem is to addressing or the control, the pixels, all the pixels. The pixel number is so high, so it's very difficult to control for example, 60 frames per second. So,
yeah, I see.
Yeah.
So maybe I have a last question is about the commercial purpose of the 3D display. Actually, they have two way. I mean, so one way is based on the LCD plus the lenticular lens technique. Another way is a holographic display, 3D display. So actually, I also saw a lot of research done by your colleague, maybe it's a Nam Dong Kyung. So actually, they pick up the lenticular super multi-view 3D display. So from your point of view, which way will be the better way to promote the 3D display in future market?
You mentioned about light field display.
Yeah, exactly.
Yeah, light field. I think light field display is one of the promising candidate for 3D display, but the problem is it is based on the ray. So after how to say the distance from the display, it depends on the distance from the display. Object can be blurred in this case because it's based on the ray. Ray cannot tightly focused on in the long way. Finally, ray should broaden. Even though you use laser light, then in that case, you also have some enlargement in the laser spot. So that means you cannot get the very high confined 3D pixels out of the screen. So for the light field display, you can only make good image quality near the display position. But the holographic display, you can make it further. So I mentioned the interactive display. In that case, 3D object, virtual 3D object should be come out of the display quite a lot. So in that case, light field display cannot do that, but holographic display can do that. So that kind of application, holographic display should be the best one, I think.
I see. So actually, how is the depth of field of your holographic display? I mean, the data you showed us.
In the paper, the viewing distance is 1 meter, and we can extract the virtual image from the display is 50 centimeter is okay. But it depends on the light sources. If you use quite good light sources, then you can extract more. I would say the distance from the display can be increased.
Okay, I see. Thank you very much.
50 centimeters for now.
Okay,
I see.
so we have quite intensive questions from one person, and do we have other people who would like to ask questions?
Yeah, I would. Hi. Hi, Dr. Lee. Thank you for the presentation. Very great. One question about the light source you were mentioning now. So when you mention about a good light source, were you referring on lasers? And you also mentioned that ideally we want to have an array of pixels to make sure that they are not to break a bit the coherence. Can I ask you what is the output power required, and would be good to have like a tunable laser to kind of break somehow the coherence and reduce also the speckle effect. So
sorry, one question is
the output power necessary, and another one is if somehow a tunable laser, maybe also via MEMS, might work well for this kind of applications.
Tunable laser.
Yeah, which might shift the wavelength very rapidly.
You
to
mean
try to
RGB?
Reduce the coherence. No. So yeah, maybe RGB. I mean, also on single device.
You mentioned about the wavelength tuning very fast.
Yeah,
to reduce the speckle.
Yeah.
The first question about the power is right now we use a few watts laser for each color. Yeah, a few watts, but because it's very inefficient structure we use. I already mentioned 10 to the -6 efficiency, but it's okay because we gathering all the lights from the display to the eye, so we have no loss of light. So 10 to the -6 is still enough to make 100 nits. But the efficiency itself is very low. So we use a few watts for each color is okay to make. I remember 400 nits in white. And the other question is about speckle reduction using tunable laser. I'm not sure, but I think the main principle of reducing speckle is mixing the modes. So in tunable laser itself is just one wavelength per each time. So it's I think it's not works well. I'm not sure.
Okay, and in that work that also you mentioned, there are also some attention on the S-LEDs, which are less coherent, superluminescent LEDs, which are less coherent than lasers. So are they? So then you mentioned that probably an array of pixels will be better. So why S-LEDs is not the favorite approach?
S-LED is a good way to reduce speckle, but anyhow it degrades the sharpness of the image because it's a trade-off between speckle and sharpness. So I think the best way to make a perfect light source is reducing speckle at the same time make sharpness. Okay. So that's why
mixing a coherent light source somehow.
Right.
Okay, thank you. Thank you very much.
Thank you.
Thank you. Any other questions? I have one question. I think you covered quite a lot about the things, but so far it seems the technology can get to from a single viewer by processing the data. What do you think is the biggest hurdle for multi-viewer?
That's a very difficult question. It depends on the pixel pitch to widening the viewing angle. So it's very hard to do for multi-viewer. But if we make a good high frequency deflector, then we can divide the direction of light to each viewer very fast, then it can be possible. I think that's the one way we already think about for the holographic TV. So in that case, we need many people to see. So for the mobile, tablet, smartphone, is personal device. So one viewer is okay, I think.
Yes.
But the TV, monitor, something like that is many people have to see simultaneously. So in that case, we use time multiplexing. If we have fast enough SLM and fast enough beam deflector, then you can do that. But it's definitely difficult approach, I think.
Thank you very much. Any other questions? If no further questions, let's thank the speaker. Thank you very much, Professor Lee. Yeah.
Thank you.
Yeah. So this is the time we concluded this Cape Advanced Technology lecture. And thank you very much for Professor Hong-Seok Lee from Korea to give this fantastic, inspiring talk. Thank you very much. And thank you all for attending this. Thank you.
Thank you very much.
Thank you, Professor.
Thank you.
Thank you. Bye-bye.
Thank you.
Thank you.
Bye.
감사합니다.
감사합니다.
Okay, Hong-Seok, I will look forward to see you in Cambridge. Yeah, please let me know before you come over. Yeah.
Yes, I will let you know.
Yeah. Thank
Bye.
you very much. Yeah. Have a very good day. Yeah. Bye-bye.
Thank you.
Bye-bye.